Okay, so the way you're going to be thinking about this position time, velocity time, acceleration time for this worksheet, you're basically going to be converting a position time graph. You're given a position time graph, and you're going to convert it first into a velocity time graph. And then once you have that done, you're going to convert the velocity time graph into an acceleration time graph. So you go from one graph to the next graph to the next graph. Now, to do this, you have to know what slope tells you for each of these graphs. What is slope telling you? You could think of this as like a slope worksheet. On a position time graph, so position is measured in meters, time is measured in seconds. What is the slope? So I'll pick 2 points on this graph. What is the slope of a position time graph? Well, let's figure it out, because I don't want you just memorizing. This is something that you should not just like have in your head and you don't really know why it is that way, but you memorized it. Don't memorize this. You should figure it out. So slope is rise over run. So what is rise measured in? Meters. What is run measured in? Seconds. So slope is meter per second. And what is meter per second? Velocity. Slope is velocity. Okay, so what do we notice about this first graph here? Is this line here, does it have a constant slope or a changing slope? A constant slope. So constant slope, if the slope is constant, then the velocity is constant. So this graph represents constant velocity. Now, what's another name for constant velocity? This is super duper duper important. Another name for constant velocity is zero acceleration. A equals 0. Okay? Now why is that important to know? Because when you're doing a homework problem or you're on the quiz Thursday, and if the problem says that the object moves with constant velocity, you go, oh, constant velocity, A equals 0, and then that's going to help you out with the 4 kinematic equations, right? Then you know one of those variables, A equals 0. And it might be expressed differently, instead of constant velocity, maybe it might say uniform speed. That'd be pretty much the same thing. Uniform speed, constant velocity. All right, so constant velocity, what's the slope of this line, roughly? Don't get too nitpicky here. What we're looking for is the general shape of this velocity time graph. So what is the slope of this position time graph roughly? About 1. So this graph's going to be like this. Just draw a straight line at 1. That make sense? Okay, so now let's go from velocity time to acceleration time. So velocity is meter per second, time is second. When you're on a velocity time graph, what does the slope tell you here? Well, rise is measured in what? Meters per second. The run is measured in seconds. So that gives us meter per second squared, which is the unit for acceleration. The slope is the acceleration. So basically the way you're going from one graph to the next is by analyzing the slope. Or if you're in calculus class, and this is not calculus-based physics, if you're not in calculus, you don't have to panic. But what's the calculus term for this? Going from one graph to the next. The derivative. This graph is the derivative of this graph. Derivative is a fancy name for slope. All right, so what do we notice about the slope of this line right here? It's 0. And didn't we say a minute ago, constant velocity is the same as 0 acceleration? The acceleration is 0. Okay? So any questions here? Let's go to the next one. So this is the easiest of all 6. This is the easiest one. Next one. So here, now guys, this is what you should have for your car lab. For your toy car lab, if it accelerated, if your car went faster, 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 your position time graph should look like this. How many of you got a graph that looks something like that? That's what you should have. If your car did not accelerate, if your car just moved with constant velocity, then you're going to have the previous one. This is what your graph would look like if it just kind of moved with a constant speed. All right, but either way, you know, don't go back and redo it if it moved at constant speed. Okay, so what's happening here? So the graph starts out, what's the slope when the graph begins? Pretty much 0. The slope starts out at 0, and then what gradually happens? The slope gets bigger. The slope gets bigger, 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 and if the slope is getting bigger, 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 then what's happening to velocity? It's getting bigger, bigger, bigger. Okay, so how do you plot that down here? I'm going to give you guys a couple minutes, so try this on your own first. Okay, so here we have a increasing slope. Now, like I said, this is very similar. This is what you should have gotten if your car accelerated in the toy car lab. And if you look at number 8 on the lab, what it tells you to do is take your position time graph and pick 7 to 10 points. Okay, this is exactly what we're doing right here. So we'll go 1.1, 0.2, 3, 4, 5, 6, and I know, squeeze one more in there. It doesn't have to be 7, but you know, there's points on the position time graph. And for each of these points, the lab wants you to find the velocity of the car. So for example, right here, this point right there, how could we find the instantaneous velocity at that specific time? You draw a tangent line. So the first, you go like this. With using a ruler, I'm not going to use a ruler here because I can't. But using a ruler, as best you can, you draw in a tangent line at that point. Okay? If you take the slope of that tangent line, that's going to give you the velocity at that point. Does that make sense? So for number 8, you're going to make this data table, time and velocity. And then these times are the times that you picked. Those are the 7 to 10 points that you picked. And then the way you find the corresponding velocity is by doing tangent lines and taking the slope. Does that make sense? So you're going to do a bunch of tangent lines. Remember I told you for the position time graph, make it big. You don't want to do a little tiny position time graph. I told you to do a full page, because if your graph is too small, it's going to be super hard to do all these tangent lines. And your graph's going to get messy. This is going to get messy because you're going to do tangent line there, tangent line there, tangent line, tangent line. You have all these tangent lines in there. And then take the slope. Number 9 on the lab, what it wants you to do is you're going to take this data table that you created in number 8 and you're going to plot it. So you're going to have velocity on the y, time on the x, and what should the velocity time graph look like? It's going to be a straight line. What you should get is a straight line like that, which makes sense because if you think about it, what is gradually happening to our slope here? On the position time graph, what's gradually happening? The slope is getting bigger, and if the slope is getting bigger, what's going to be happening to the velocity? It's going to be getting bigger. So when you connect the dots, it should be a straight line. Okay? All right. Now, velocity time to acceleration time. What do we notice about the slope here? Is it positive or negative? Positive. Constant or not constant? It's constant. And roughly the slope is 1. So this would be an acceleration time like that. It's a constant positive acceleration. Okay, last one. So here we start out with pick a point right there. we start out with a pretty big velocity, and then what happens by the time we get over here? The velocity is almost zero. Okay? So if you want to be real thorough, you could pick multiple points. Pick multiple points, do tangent line, tangent line, tangent line, take the slope of those, and what you're going to find is you're going to get something like this. Your points would kind of fall like this. The velocity is gradually decreasing, like that. Okay? What's the slope of this line? Positive or negative? Negative. What's the slope roughly? It's less than 1. So I don't know, even less than 1/2. Somewhere in here. Don't get too caught up on perfection here. We're just looking for the general shape of these graphs. Okay? So try the next 3. I'll have the solutions posted on the website so you can check them out. Any questions? Okay, so you guys have the rest of the period to work on lab, on homework. I'll cruise around and help you, whatever you're stuck on. And tomorrow we'll check homework. Thursday's the quiz.